Hi, this lecture will be on continuous time Markov chains. We are going to begin with an example, which is the Poisson process. This is in fact the most important example of a continuous time Markov chain and will play a very important role throughout this course. So it's important to make sure you understand the Poisson process deeply. And once you do that, the general continuous time setting is just a variation on the theme. Okay, so I'm sharing screen with you now. So let's start by defining what is the counting process first. So this is a stochastic process. Time is going to be continuous for us, so t will be in the positive reals. And this event n of t counts the number of occurrences of something until time t. Without loss of generality, let's start with n naught equals 0 and then count up to time t how many events have occurred. So this count is always going to take integer values, and it is also going to be a non-decreasing function of time because the number of occurrences of an event of interest up to a later time cannot be less than up to an earlier time. The next property, so a process, not necessarily a counting process, is said to have independent increments if the increment of the process between time s and some later time t, so the amount by which it's increased from s to t, if this is independent of everything that happened in the past up to time s. So it's independent of the process up to the time s. Okay, so now we are ready to define a Poisson process. So a counting process n, so to be a Poisson process, it firstly has to be a counting process. It has to have independent increments. And in addition, it has to satisfy one of the following equivalent statements. Okay, so firstly, so the increment nt minus ns is independent of the past, but that's not enough to fully characterize it. So one way to characterize it would be to specify its distribution. And if the distribution of this random variable is Poisson with parameter lambda times t minus s, then this is called a Poisson distribution. And you can see why it gets this name. It comes from the Poisson distribution of the increments. What's lambda here? Lambda is just some positive parameter which will be called the rate or the intensity of the Poisson process. So just like a Poisson random variable is parameterized by its mean, the Poisson process is parameterized by its rate or intensity. So that's one way to define a Poisson process. Here's another way. Instead of saying what the increment distribution is over an interval of some finite size, t minus s, we can describe what its distribution is over an infinitesimal interval, a very small interval of time. And so for a Poisson process, the following is true. If you look at the change from time t to time t plus delta, and you should think of delta as a very, very small time increment, then in this increment, the process can increase by 1. You can see exactly one event, and this happens with probability lambda times delta. So it happens with probability which is proportional to the length of the interval, with proportionality constant, which is the rate. Okay, maybe a concrete example is worth keeping in mind. So let's say you are driving along the motorway and you are counting the number of cars passing in the opposite direction. So that counting process is nt. So the number of cars you see up to time t is necessarily non-decreasing. And then for it to be a Poisson process, it has to have one of these properties. So the probability that in the next 1 second you see a car going past is your intensity lambda times delta, which is 1 second. And then this little o of delta, we'll define it more formally on the next slide, but intuitively you should think of it as something much smaller than delta, vanishingly small compared to delta. Okay, so maybe delta squared or delta cubed or something like that. Okay, so the chance of seeing another car in the next delta time units is lambda delta. The probability of seeing no cars in the next delta time units is 1 minus lambda delta, again up to some small error term. And the probability of seeing 2 or more cars within a very small time interval is 0. There are gaps between cars, and you cannot see 2 of them passing by simultaneously in a very tiny amount of time. Okay, so if the process satisfies these properties, that's another way to describe a Poisson process. And the last way is in terms of the times between successive increments of the process. So if you look at when a car passed, and then how long is it till the next car goes past you, that time interval has an exponential distribution. Recall that this is a continuous random variable, time is continuous, and so that's what we should expect. And now this is an exponential distribution with parameter lambda. Okay, so you should recall that this has mean 1 over lambda. So lambda being very big means that these events are happening very fast. So the gap between them is small, and the number of events that happens in a given time interval is large. Okay, and it's not immediately obvious that these three statements are equivalent, but there's a proof in the lecture notes that you can look at, and we can use any one of these to define the Poisson process. And as I already mentioned, the process is governed by this parameter lambda, and that's called the rate, its rate or intensity. Okay, so I hope the definition of a Poisson process is completely clear. So let's look a bit more at this little o notation and some more asymptotic notation that we'll be using throughout this course. Let's say we have two functions f and g, which map the positive reals to the real numbers. We say that f is little o of g at the origin if the following is true. If the ratio of fx to gx tends to 0 as x tends to 0. In other words, if f goes to 0 faster than g goes to 0. Okay, or no, they needn't go to 0. If f is small compared to g at the origin, then we say f is little o of g. We say f is capital O of g if f is not growing faster than g. It may grow at a comparable speed to g, or it may be vanishing as with the little o notation. So more formally, f is capital O of g if there's a constant, positive constant c, such that f of x is bounded by c times g of x in some neighborhood of the origin. Okay. And similarly, we may not be interested in what happens at 0. We may be interested in what happens at infinity, and little o and capital O are defined in exactly the same way at infinity. And finally, we use little omega and capital omega to denote the opposite of little o and capital O. So we say f is little omega of g if g is little O of f, and f is capital omega of g if g is capital O of f. And as usual, let's look at examples to help make this clearer. So let's take fx to be x, gx to be sine x, and hx to be x squared. So what happens to f and g at the origin? Let's look at the ratio x over sine x. If you look at the Taylor expansion of sine x, you'll see that the leading term in it in x. So this ratio, in fact, tends to 1 as x tends to 0. Or using L'Hopital's rule, you can check the same thing, that it tends to 1. So f is not little O of g, g is not little O of f, but g is capital O of f at the origin, and f is capital O of g as well. Okay. And what about at infinity? At infinity, x goes to infinity, sine x is bounded, so g over f goes to 0, so g is little O of f at infinity. Now what about h? H is x squared, so if we look at the ratio hx over fx, that's x squared over x, that goes to 0 as x goes to 0. So h is little O of f at the origin, and h grows faster than f at infinity. H over f goes to infinity, so h is omega of f at infinity. Okay, so that's all the asymptotic notation we need. So we are often going to be interested in comparing two functions and how quickly they grow relative to each other, either near the origin or near infinity. And it'll be often clear from context whether we are interested at the origin or at infinity. So when it's clear, we won't say explicitly at 0 or at infinity. Good, so that's some notation. Let's come back to the Poisson process. Let's look at a picture of what a sample path of the Poisson process looks like. Okay, so this is what the picture looks like. The Poisson process starts at 0. It stays at 0 for some time, some random time. It jumps to 1, stays at 1 for some random time, jumps to 2, and so on. So it's a counting process. It counts the number of occurrences of something up to time t. So it's an increasing sequence of natural numbers. A couple of things to note. The process can only jump by 1 at a time. It can't jump by 2 or 3. So you never have simultaneous occurrences of 2 or more events. That's not for any counting process. That's a property of the Poisson process. So in terms of the definitions, what are we saying? If you look at some time s here and some later time t here, and you look at how much the process has increased over this time interval, that increase is a random variable with a Poisson distribution. That's one way of describing it. And the other is to look at these times when the process increased. So this is T1, T2, T3, and T4. And these, so T2 minus T1 is an exponential random variable with parameter lambda. T3 minus T2 is an independent exponential with the same parameter. T4 minus T3 is an independent exponential with the same parameter, and so on. These are IID exponential lambda random variables. Okay, so that's the picture of a Poisson process. There are a couple of properties of the Poisson process that are, in fact, 3 properties that are going to be important throughout the course. So the first is that if you have a Poisson process with a given intensity lambda and some positive constant beta and you rescale time, so you speed up time by beta, then the process you get by doing that, so n of beta t is what you get if time runs faster by a factor beta, then that's also a Poisson process. So if you take a Poisson process, change the units in which you measure time, you get another Poisson process. And that Poisson process has intensity beta times lambda. Okay, so that's the first property. The second property says that if you take two independent Poisson processes with intensities lambda 1 and lambda 2, and you take the superposition of them. So you N1 has a sequence of times at which events occur in that process. N2 has a different sequence of times at which events occur. And you put these two together. You count events of both types. Then that superposition is another Poisson process as well, and its intensity is lambda 1 plus lambda 2. Okay, if that's maybe a bit abstract, let's go back to our concrete example. So we are counting cars that we pass on the motorway. So suppose N1 counts all the red cars that we pass, and N2 counts all the blue cars that we pass. And N1 plus N2 counts all the cars that are either red or blue. Now, if red cars pass us according to a Poisson process of rate lambda 1 and blue according to pp lambda 2, then the number of cars which are either red or blue that pass us is also a Poisson process, and its intensity is the sum of the intensities. That's what this is saying. And the first statement is saying that if we count, if the rate is, if the number of cars is a Poisson process when we count time in minutes, it's also a Poisson process when we count time in seconds, but the intensity changes. Okay, so hopefully those two statements are clear. We haven't proved either of these. The proofs are going to be a homework problem. So you will prove these using the definition of the Poisson process we saw earlier. The third property, which is a bit more subtle. So for the second property, we took two independent Poisson processes and combined them, and the combination is Poisson. Now we are going to take one process and split it in two. And we are going to split it in this somewhat non-obvious way. So what do? We have a Poisson process with intensity lambda, and we have a sequence of Bernoulli random variables. So let me remind you what a Bernoulli random variable is. This is a random variable which takes values either 0 or 1. It takes value 1 with probability p and 0 with probability 1 minus p. Or if you like, think of it as a coin toss. The coin comes up heads with probability p, tails with probability 1 minus p, heads count as 1, tails count as 0. So that's a Bernoulli sequence. So we have a Poisson process n, and we have a sequence of Bernoulli random variables, which is independent of our Poisson process. And we are going to use this to split our Poisson process. So how do we do this? Every time we see an increment in the Poisson process n, we assign it randomly to either n1 or to n2. So when we see an increment, we toss a coin. If it comes up heads, we assign it to n1. If it comes up tails, we assign it to n2. So n1 and n2 are counting processes, clearly. And they are called the Bernoulli thinnings or splittings of the process n. And the claim, and this is not obvious, of course, this is the important property. The property is that N1 and N2 are themselves Poisson processes. They are independent of each other, and they have respective intensities lambda times p and lambda times 1 minus p. Okay, so take a moment to make sure the statement is completely clear. Okay, that all three statements are completely clear. And the proofs of these statements are going to be homework problems. So let's see. Okay, the first statement I won't show in pictures, but let's see the second and third in pictures, what we are trying to say. So here we have the blue and red process. So we are counting red cars and blue cars that we pass on the motorway. So time starts at 0. I've run them one on top of the other to make it visually clearer, but all these are 0, all these are 1, all these are 2, etc. So red, blue, and black all start at 0. And then at this time, we see the first red car, so the count of red cars goes up to 1. At this time, we see the second red car, the count of red cars goes up to 2. At this still later time, we see the first blue car, the count of blue cars goes up to 1, then the count of blue cars goes up to 2, then the count of red cars goes up to 3, and so on. The black lines count cars which are either red or blue, so they start at 0, goes up to 1 when we see the first red car, to 2 when we see the next red car, 3 because we then see a blue car, we see yet another blue car, it's gone up to 4, red car, it's gone up to 5, and so on. Okay, so this black process N is the superposition of N1, the red process, and N2, the blue process. And the claim is that if the red and blue processes are Poisson, then so is the black process. So that's that superposition. And this is the picture of splitting. So again, we start with all of them being 0 in the black process. Then the black process goes up by 1. And now we toss a coin. And the coin comes up heads. So we assign the first jump to the red process. So the first jump of the black process goes to red. So the red process goes up to 1 here. At the next jump of the black process, which happens at this time, we toss the coin again, we get tails. So we assign it to the blue process. So the blue process goes up to 1, and at the same time, the black process goes up to 3. Goes up to 2. And now at this time, the black process gets another jump, goes up to 3. The coin toss comes up head, so we assign it to red, which goes up to 2. The black process gets another increment here, goes up to 4. Toss the coin again, comes up heads again, so we assign it to red, it goes up to 3. The next jump of the black process, we toss the coin, get a tail, assign it to blue, and so on. Okay, so we have constructed the red and blue process by randomly assigning the jumps of the black process to one or the other. And the claim is, if we do this, the red process is Poisson, the blue process is Poisson, and the red and blue processes are independent of each other. Okay, and I hope that statement of that claim is completely clear. At this point, you might well have a question of why we do the splitting in this strange way. There's a much more obvious way to do the splitting. Take the original Poisson process, the black process, and alternately assign them to the red and the blue. Okay, that's the most obvious thing to do. And does that give us two Poisson processes of intensity lambda over 2 if we do that? It doesn't. I claim that it doesn't, and this is how to see it. So suppose we do that. Suppose we assign alternate jumps of the black process, red, blue, and so on. So let's see what happens at the first jump. It goes to red. Second jump goes to blue, just as we had. Third goes to red. Now fourth for us went to red, but it should go to blue. And so you get different processes. And why is the red process now not a Poisson process? And likewise, why is the blue process not a Poisson process? Let's look at the time between two successive increments of the red process. So the red process goes up here and it goes up here. So what needs to happen between between successive increments of the red process? Well, we must have had two increments of the black process because only alternate increments are assigned to the red process. So we must have had two jumps of the black process in order to see one jump of the red process. What's the distribution of the increment times between the black process? It's exponential lambda. That was one of our definitions of the Poisson process. So in order to have an increment of the red process, we need to add two independent exponential lambdas. And what do we get if we add two independent exponentials? We don't get another exponential. We get a gamma distribution with shape parameter 2 and scale parameter lambda. Okay. So the important thing is that it's not exponential. And that means, by the definition of a Poisson process, the red process cannot be Poisson because the time between successive jumps of the red process is gamma. It's not exponential. Okay, so the obvious way of splitting a Poisson process doesn't yield another Poisson process, but the Bernoulli splitting does. Good. Okay, so that's all I wanted to say about the Poisson process. As I say, this is the most important example of a continuous time Markov chain we are going to look at. And you should make sure you understand it well, and that will help you understand the more general setting. The homework problems should help you with that by asking you to prove various things we stated as properties. So let's take a break here and we'll continue with the general setting next time.